OCR Chemistry A, Compounds, Formulae and Equations. Getting the best from Chemistry Explained needs you to participate, so write notes, complete tasks on paper or tablet. Pause and control the pace at which the lesson goes. Crucially, complete the tasks when prompted. That means pausing the lesson, taking your time, thinking the problem through. Only when you're ready, continue. Correct your work before moving on to the next slide. So the topic overview, we're going to start with ionic compound formulae, move on to writing balanced equations, apply state symbols, that's very simple, but then move on to ionic equations, how to derive them from balanced symbol equations. So, ionic compound formulae. The ion charges in an ionic compound sum to zero. That is the crucial idea. So let's apply that to a couple of models, sodium oxide and calcium hydroxide. Well, we know that the sodium ion is a 1 plus ion, Na plus. We know that the oxide ion is a 2 minus ion. Well, a single sodium ion and a single oxide ion, the charges do not sum to zero. We need a second sodium ion. So 2 1 plus ions and an oxide ion at 2 minus, the charges sum to zero. So we conclude that the formula of sodium oxide is 2 sodiums, Na2, and 1 oxygen. So let's take another example, calcium hydroxide. So calcium, a 2 plus ion, hydroxide, 1 oxygen, and hydrogen, OH, is 1 minus ion. For the charges to sum to zero, end of the lesson. For the charges to sum to zero, we need 2 hydroxide ions at 1 minus each, so that the 2 plus ion and the 2 hydroxide ions, those ion charges sum to zero. So we write that as a formula in this way, 1 calcium and 2 hydroxides within the bracket. So the question that comes up is, how do we know the ion charges? Well, there's a very simple guide, a helpful guide in the periodic table, of course. The group number in the periodic table, so group number 1, sodium, potassium, in their compound, the ion charge is 1 plus. So group number 2, magnesium and calcium are examples, they form 2 plus ions in their compounds. Group 3, aluminium, is a 3 plus ion. There's a pattern, I'm sure you're picking up. Group 5, we start forming negative ions, nitrogen and phosphorus, both form 3 negative ions. So 3 negative. Group 6, oxygen and sulfur form the oxide and sulfide ion at 2 negative, 2 minus ions. Group 7, chlorine, bromine are examples, 1 minus ions. We've also got to consider group ions. We met the hydroxide ion on the previous slide. So the hydroxide ion is always an oxygen and a hydrogen, and it's got a 1 minus charge. The nitrate ion is always 1 nitrogen and 3 oxygens, and it's again a 1 minus charge. How do we know this? I'm afraid at this stage of your A-level course you have to memorize these group ion formulae and charges. So the carbonate, CO3, a 2 minus ion, the sulfate, SO4, is a 2 minus ion, and the ammonium ion, NH4, is a unipositive, a 1 plus ion. So most of these group ions are negative, but we have, for instance, here the ammonium ion as a positive ion, 1 positive. So we move on to use our knowledge of ion charges set out in these tables to produce the formulae. Okay, so here are some ionic compounds for which I'd like you to write the formulae. Try that now. Pause the video and try that now. So continuing, I'll just go through as an example. Sodium is a +1 ion. Iodide is a 1- ion. You notice those, one of each sums to 0, so sodium iodide is the correct formula. So what about zinc chloride? Well, zinc is a 2+ ion. It's a transition metal. I think that popped up on the slide earlier. I forgot to mention it. Transition metals we can assume to be 2+. Chloride is 1-. Well, we're going to need two 1-. 2+, 1-, 1-. Well, that's all going to sum to 0. We add those all together, it's going to come to 0. So zinc chloride would be written as ZnCl2, 1 chlorine and 1 zinc and 2 chlorines. And third problem, I'm going to take you through aluminium oxide. Well, aluminium is a 3+ ion. Oxide is a 2- ion. Well, those 1 to 1 doesn't sum to 0. So what if we have 2 aluminiums and 3 oxides? Well, that will sum to 0. So we write that as aluminium twice and oxygen 3 times. Okay, so would you like to try the remaining problems here? Try those and then pause the video, try those and then come back in a moment or two when you're ready. So here are the answers. Calcium sulfide, 1 calcium, 1 sulfur. Silver iodide, 1 silver, 1 iodide. Barium bromide, BaBr2, MgO, Li2O, ZnO. The one that may have caused you problems is magnesium nitride. I may just go through this just here, so I've got a moment or two. Magnesium 2+, 3 magnesiums at 2+, and 2 nitrides at 3-. Hope you can see that will sum to 0. So magnesium nitride is 3 magnesiums and 2 nitrogens or nitrides, Mg3N2. So let's move on to some problems that involve group ions. So the first one we're going to look at here is sodium hydroxide. So sodium, we know, is a 1+ ion. And the hydroxide ion, OH-, look back at the previous slide if you're not clear, OH-. So if we have 1 sodium and 1 hydroxide, we'll see that those sum to 0. So our formula is sodium hydroxide. Okay, so there's sodium hydroxide. Pause the video and write the correct formula for sodium sulfate. Okay, so sodium is a 1+ ion. Sodium is a 1+ ion, I've said that already. The sulfate is a 2- ion. So we need 2 sodiums to sum to 0 with the sulfate ion. So my formula for sodium sulfate, Na2SO4. So pause the video and try now for aluminium sulfate. I misspoke, aluminium nitrate is the next example. So aluminium, group 3, is a 3+ ion. The nitrate, if you don't know, you need to know, is NO3 1-. So a little bit of shorthand, I need 3 nitrate ions so that the ion charges sum to 0. So I write that as aluminium, bracket, nitrate, 3 times. So there is aluminium nitrate tidied up. Pause the video and try the remaining named compounds as formulae. And here are the correct answers. Check those please before you proceed. If there's any errors, go back and look through the previous slides and have another go. Having achieved correct compound formulae, we can now move on to writing balanced chemical equations. Now, balancing equations, I'm sure you've met balancing equations before, but the basic idea is that the numbers of atoms or symbols on the left-hand side, the reactants, equals the numbers on the right. We don't create or destroy atoms in a chemical reaction. So let's look at an example. Calcium carbonate and hydrochloric acid, or HCl, gives us calcium chloride, water and carbon dioxide. Now the balancing number is the 2 that goes in front of the compound formula. We've got 1 calcium, we've got 1 calcium, so we're balanced for calcium. We've got 1 carbon, we've got 1 carbon. We've got 3 oxygens, well we've got 1 oxygen here and 2 oxygens here. We've got 2 chlorines on the right hand side, well without that balancing number we'd only have 1. That 2 multiplies by 2 the whole formula. So here we have 2 hydrogens and 2 chlorines. So I've got 2 chlorines on the right hand side by balancing my multiplier or my coefficient here. Okay, I've now got 2 chlorines. I've also got 2 hydrogens, and oh, I've got 2 hydrogens on the right hand side. I am balanced. So one thing I didn't do when balancing was change the formula of the compound. The formula of the compound is determined by bonding theory, or alternatively a theory of valency. So the formula of hydrogen chloride is always HCl, regardless of which equation it appears in. But we can have 2 molecules of hydrogen chloride. And by having 2 molecules of hydrogen chloride, we of course double the amount of hydrogen and chlorine. So to balance, we use the coefficients, the large balancing numbers in front of a formula, and that multiplies the whole formula. We cannot change the formula itself. That is determined by bonding theory. So I'd like you to pause the video and try the first balance the first equation in this sequence. Okay, so I'm assuming you've tried to balance this equation. You'll see straight away that we've got a problem here. We've got 2 hydrogens. Well, we've only got 1 here, so we need to use a multiplier to change the numbers of hydrogens. But we've also therefore got 2 nitrates, which we keep as a radical or a unit, and we'll see we've got 2 of them here already. We've got 1 copper on 1 copper, 1 oxygen and 1 oxygen here. So the balancing simply requires a 2 in front of nitric acid, HNO3, or hydrogen nitrate if you prefer. So I'd like you to pause the video and try the second equation. So resuming, we'll see straight away we've got a problem in that we've got, or the problem is, as far as balancing is concerned, we've got 2 sodiums on the right hand side, we've only got 1 on the left, so we need to use a balancing number, a multiplier in front of the sodium. We've got 2 hydrogens on the left, we've got 2 hydrogens on the right. We've got the sort of radical sulfate or group ion sulfate, which we have also here. So the only balancing required is to give us 2 sodiums on the left hand side. Everything else is now balanced. So pause the video and complete the other equations, please, or balance the remaining equations. check your answers against these here. Pause the video if you need and check your answers before going on to the next slide. Now, very often at A-level, rather than giving you the formulae and the complete reaction equation to balance, you simply, as one would in a lab, add magnesium to hydrochloric acid and you have to derive a chemical equation for that. So let's take an example. You need to get both the formulae of the reactants and you need to identify the products. Well, that would be magnesium chloride. I need to know the formula of magnesium chloride. Magnesium is a 2+ ion, chlorine is a 1- ion. You've got to go through that and be secure with all of that. And the other product is, of course, hydrogen gas. So I now need just to balance that equation. Having written out the correct formulae for the correct products, I now need to balance. You'll see I've got 2 hydrogens here on the right. I've only got 1 on the left. So I need a balancing number here for 2 hydrogens. That also gives me 2 of everything. So I've got 2 chlorines as well. And on the right hand side, I already have 2 chlorines. So that is now the balanced equation. So take your time, think it through, pause the video and complete the other equations, please. So here are the correct answers. Please check your answers against these. The zinc oxide and sulfuric acid goes to zinc sulfate and water. Sodium carbonate and 2 nitric acids go to 2 sodium nitrates, carbon dioxide and water. And of course you must get the formulae of the compounds correct. The covalent molecules such as carbon dioxide, H2O, I hope you are familiar with, or you are expected to be familiar with and get correct. Anything that is based on ions, for instance sodium nitrate here, well, we get that by the work we've done earlier on this lesson, making sure that the ion charge is summed to 0. So you may need to refer back if you're making any mistakes. Moving on, 2 sodium hydroxides are required and 2 moles of water are also produced, and then to make ammonium sulfate, 2 ammonias. So moving on from balanced equations, a quick review of state symbols. Another feature of chemical equations which you will have met is state symbols. So G for gas, L for liquid, S for solid, and AQ for dissolved in water. Aqueous solution means the substance is soluble and it's formed a solution in water. Aqueous solution, AQ. So we apply those to equations such as this model here. So calcium carbonate here is of course a solid. HCl, hydrogen chloride, is an aqueous solution, otherwise known as hydrochloric acid. Calcium chloride forms an aqueous solution, we are told, because of the state symbol. Water is not written as a solution. Of course, it's a liquid in which other substances dissolve. It is a solvent. So liquid for water, and the gas carbon dioxide. Now, state symbols have been not strictly of great importance up to this point, but we're now going to move on to our ionic equations, and here you'll find they are a key element to writing the correct equation if asked for an ionic equation. So moving on to ionic equations, in which we're going to use both balanced equations and have a particular use for state symbols. So the preparation for ionic equations has been completed. We can now move on to those. So ionic compounds dissociate when in aqueous solution. This is the key idea behind ionic equations. What do I mean by that? I mean that something like sodium chloride, NaClAq, doesn't exist as a NaCl unit in a solution. It exists as two free dissociated ions moving independently of each other, randomly and extensively. So we would need to realize that sodium chloride AQ is actually forming a solution that contains separate sodium ions and separate chloride ions, what we call dissociated ions. Now, when we come to look at a few examples, we will see that we can use the term spectator ion. Some of those ions are simply watching other ions change. And the key element of an ionic equation is that the spectator ions are left out or removed from the reaction equation. So we just focus in on those ions that are changing. Those ions that are remaining unchanged are spectating, they're not included in our equation. So we're going to see the significance of state symbols when we move on to writing ionic equations. So let's take a simple example to start with. Best start with a simple example. Sodium chloride and silver nitrate, we mix those together, we get a precipitate of silver chloride as shown by the state symbol S, and a surrounding solution, an accompanying solution of sodium nitrate. Now, as I explained on the previous slide, sodium chloride is going to dissociate into its ions. Silver nitrate is going to dissociate into its aqueous ions. Silver chloride on the right-hand side does not do that. It's a solid, so it is insoluble and the ions do not dissociate. However, silver nitrate is soluble, forms an aqueous solution, so again it will dissociate into free aqueous ions. So what I'm going to do now is identify the spectator ions by putting a red line through them. Well, we'll see on the left hand side that we have a sodium ion, and on the right hand side we have a sodium ion. So they haven't chemically changed. The arrow implies chemical change. Sodium ions, aqueous sodium ions, have not changed. We see that the nitrate ion exists on the left hand side and on the right hand side as a free aqueous ion. Again, they have not changed. The only things that have actually changed are the aqueous chloride ion, the aqueous silver ion, to form a solid precipitate of silver chloride. So our ionic equation removes the spectator ions, and we are left with Ag plus Aq plus Cl minus Aq going to AgClS. The change in state is absolutely crucial. If AgCl was aqueous, then there would have been effectively no chemical change on mixing the two solutions. Only because silver chloride is a precipitate is there a chemical change, or is insoluble, causing a precipitate and therefore a chemical change. So moving on to some problems. Could you write ionic equations for each of these two full chemical reaction equations? Pause the video and do that now. Okay, so if I pick up and just take them as models, so silver nitrate, of course, we're going to get our silver ion and our nitrate ion, and they're going to be aqueous, free aqueous, and aqueous. We're also going to get a potassium ion and a bromide ion. On the right hand side, we are going to form a precipitate of silver bromide, but potassium nitrate is soluble, and therefore we get nitrate ions and potassium ions. Now, crossing out the spectator ions, I've got the nitrate ion left and right. I've got the potassium ion left and right. So that leaves me with silver ions and bromide ions, making silver bromide as my precipitate. So there is the ionic equation in blue there. Now, if you didn't get that right, perhaps pause the video and have another go at problem number 2. Otherwise, I'm going to go through number 2 myself right now. So, lead nitrate is of course ionic and soluble. Now I can write 2 there in front just to quantify the numbers of nitrate ions. So I've got 2 potassium ions also, 3 aqueous potassium ions, excuse my writing, plus 2 iodide ions, 3 and aqueous and 3. However, the lead iodide is an insoluble substance and therefore forms a precipitate. I've got 2 aqueous potassium ions and 2 aqueous nitrate ions. Applying the same method, crossing out the spectator ions, I've got 2 nitrates left and right. I've got 2 potassiums left and right. So that leaves me with my ionic equation. Now, as with all previous slides and lessons, find some more problems in your textbook or online and practice so that you are absolutely certain and you have consolidated your learning. Then move on to the next lesson.